Okay, let's just dive right in. Welcome to today's Explainer, where we're going to take what usually looks like an incredibly dense, highly technical subject, machine learning, and break it down into something you can literally hold in your hands. You know, if you've ever glanced at a data science textbook and felt totally overwhelmed by all that jargon, you were absolutely in the right place. Today, we're decoding those complex concepts using an everyday analogy that's, well, as satisfying as a sweet summer snack. So picture this. You're walking up to a fruit stand on a hot, sunny day. You want a watermelon, but you don't just want any watermelon, right? You want the absolute perfect one. Sweet, juicy, perfectly ripe. The catch? You can't actually cut it open to check. So what do? You probably stand there looking at it, picking it up, maybe giving it a little tap. You're trying to predict exactly what's inside based entirely on what you can observe on the outside. And honestly, this brilliantly illustrates how we humans operate every single day. When you're evaluating that watermelon, you're probably looking for a healthy green color, maybe checking if the root is nice and curly, and definitely listening for that classic, deep, muffled sound when you knock on the rind. But why? Well, because you've eaten watermelons before. Your confidence in picking a ripe one relies purely on experience-based predictions. You associate those very specific physical traits with the sweet reward of a ripe fruit, all based on your past successes. Now, we humans clearly learn from experience, but can computers do the exact same thing? The answer is a resounding yes. It's just that computer science uses a slightly different language to describe it. Take a look at this formal definition from Tom Mitchell back in 1997. I know, it sounds a bit like a mouthful, right? Experience E, tasks T, performance measure P. It feels super academic. But don't let the alphabet soup scare you off. Let's just break that textbook definition down into plain English. The crucial point is really this. Machine learning is simply a technique that allows a system to improve its performance by learning from experience. Simple as that. But for a computer, experience doesn't mean standing at a fruit stand. For a computer system, experience exists entirely in the form of data. We feed it data, and it uses computational methods to build algorithms that can make predictions. It is literally the exact same logic you use at the grocery store. It's just being processed by a machine. All right, moving into section 1, decoding the data. To make a machine understand our watermelon picking intuition, we have to translate our real-world sensory experience into the vocabulary of data science. These right here are the building blocks of every single machine learning model. A data set is just your whole collection of records. So imagine a giant spreadsheet of every watermelon you've ever inspected. An instance, or a sample, is just one single event or object. In our case, one specific watermelon. Attributes or features are simply the categories of description: color, root shape, sound. And finally, the attribute values are the specific traits for that one melon, like it's green, it's curly, it's muffled. So the next time you hear data scientists throwing around intimidating words like attributes and instances, just remember they're really just talking about the color and shape of a single piece of fruit. Now, what's really fascinating is how those simple physical traits start to look when a textbook formalizes them. You see all of these variables, right? The X's, the D's, the intense mathematical notation. I know that can instantly trigger some math anxiety for a lot of us, but I want you to strip away that intimidation factor. When you see an X with a little subscript on a page like this, it is literally just a placeholder. It's really just a formal way for the computer to neatly file away the fact that watermelon number 3 has a straight root. That's the whole shebang. And that brings us to a term you are going to hear a lot: the feature vector. Imagine you're drawing a 3D graph. One axis is for color, one is for root shape, and the third is for sound. If you take one single watermelon and plot its specific color, its specific root, and its specific sound on that graph, it becomes a single dot in that 3D space. That coordinate point, that's the feature vector. Every single watermelon you evaluate is just another point floating in that specific sample space. Pretty cool, right? Which brings us to section 2, training the machine. Okay, so we've got our data neatly organized and translated. We've plotted our watermelons in space. Now comes the really exciting part. How does the computer actually figure out the rules of ripeness? Well, think about it. If you tap a watermelon, guess that it's ripe, but then you never actually cut it open to eat it, you haven't really learned anything, have you? You need to know the actual outcome. In machine learning, this outcome is called the label, or sometimes the ground truth. In our analogy, the label is simply ripe or unripe. Without providing the algorithm with this outcome information during the training phase, the machine absolutely cannot learn an effective prediction model. It basically needs the answers to the test in order to learn the pattern. And depending on what kind of label we're actually looking for, we divide our learning tasks into different categories. If our prediction output is discrete, meaning it fits into neat, separate little boxes, like ripe versus unripe, we call that a classification problem. But what if we wanted to predict something on a sliding scale, like exactly how sweet the watermelon is on a scale of 1 to 10? Whenever the output is continuous like that, it's called a regression problem. Now, our ripe versus unripe question is a classic classification problem. And because there are only two possible outcomes, it's either ripe or it's not, it's specifically known as binary classification. One class is marked positive, the other negative. If we were trying to categorize the watermelons into, say, 3 or 4 different varieties based on their traits, well, then that would jump up to multi-class classification. This label distinction also defines the overall type of learning we're doing. When we feed our algorithm training data that actually includes those vital labels, telling it exactly which melons were ripe and which ones weren't, that is called supervised learning. We're actively supervising the learning process by providing the answers. But what if we just dumped a giant pile of watermelon data into the computer without any labels at all? The computer might notice, hey, a bunch of these are light-colored and a bunch are dark-colored, and then separate them into groups. That grouping, without knowing any inherent truth like ripeness, is called clustering, which is a prime example of unsupervised learning. And that leads us perfectly into Section 3, the real-world test. All right, so our machine has analyzed the data, it's learned the patterns, and it's formulated a solid hypothesis about what makes a watermelon ripe. But let's be real, a hypothesis isn't worth much if it only works on the past. We have to see what happens when we go back to the fruit stand and look at a brand new shipment. This is the testing phase. It is the absolute moment of truth for our algorithm. We are now taking the underlying rules the machine learned during training, its hypothesis, and applying them to completely unseen instances. We're giving it watermelons it has never ever evaluated before, asking for its prediction, and seeing if it gets the label right. And honestly, can you imagine the sheer volume of watermelons a computer would have to virtually knock on to get this right? It's pretty staggering when you think about it. And this brings us to what is arguably the single most important concept in this entire explainer: generalization. The ultimate objective of machine learning is not for the computer to just perfectly memorize the training examples. Think about it. If it just memorizes the exact traits of the 100 watermelons we fed it, it's completely useless when faced with watermelon number 101. A successful, well-generalized model discovers the actual underlying rules so that it works well across the entire sample space, especially on completely new samples. But for that generalization to actually work, we have to make a fairly big mathematical assumption. You're going to see the acronym IID a lot in machine learning texts. It stands for independent and identically distributed. In simple terms, this basically means we're assuming all our samples are coming from the exact same overall environment or distribution. We assume the rules of watermelon ripeness that applied to the ones we trained on will also apply to the ones we are testing on right now. Which leaves us with a really fascinating challenge and a thought I want to leave you with today. If our machine was trained exclusively on the characteristics of local, dark green watermelons, what happens if we test it on a striped, exotic melon from halfway across the globe? If the basic distribution of the data changes, if we break that IID assumption we just talked about, our model's ability to generalize might totally collapse. It really goes to show that a machine is only as worldly and only as accurate as the experience we provide it. So how well do you think your models are generalizing? Keep looking for those patterns, and I will catch you on the next explainer.